section is representing qubit states. There's three, like three ways that we're going to go over that can be used for representation. And this, again, this is pulled straight from the Qiskit quantum computing textbook, just kind of like my notes and summary. So like state vectors, this is what we're going to use primarily to talk about qubits. And the motivation for the use of state vectors is, I think, something that is like most important to like understanding and getting a feel for like the use of them in general. In classical representations, and again, when we talk about something classical or a classical machine, classical variables, this is like our digital computers, right? These computers that we can talk about, that we don't have to generally worry about what the probabilities are for like measuring certain states, because in fact, they're always just 100% with respect to like whatever we programmed that value to be, right? And so if we look and think about this car right here, there's a few ways to describe it, right? And classically, it's quite simple and intuitive. We would say that this car is at position 4. Out of all these possible positions, the only information that we would give to a computer or a classical machine when talking about the position of this car is we would say X, or position, is equal to 4. Because giving any more of a detailed description, we could say like, well, X is 4, but it's not 10, and it's not 9, and it's not 8. That doesn't really like give us more information. I mean, if we think about how classical machines work, it doesn't matter to a classical machine what this is not, as long as you tell it what it is. And so because of this, like this non-probabilistic, discrete manner in which states are described in classical machines, a state vector representation wouldn't make too much sense. And when we think about what a state vector representation would look like, we can look at something like this. If we were to define this on a classical machine, we could go about saying that, well, it has a probability of 1 or 100% of being at the 4th position, right? And it's got a 0 probability of being at all the other positions, right? And we've talked about this. Will has talked about this before, and we've talked about it in other lectures. And we can very easily just kind of in our minds next to each of these elements write 0, 0, 0, 1, 1, 0 in ascending order all the way to the like greatest possible state, right? And we have that as kind of this implied column right next to our state vector or our probabilities, right? And so within the state vector, it's not actually the probability, but the probability amplitude that is described. And we'll talk more about the translation between those two ideas. But we can think of it in this case as a probability, right? And we could say that there is a 100% or a probability of 1 of this car being at position 4. Again, it's the same description, but in classical machines, this doesn't really help us very much. And even in quantum machines, when we have this kind of definitive 100% probability of being at a certain position, it's not super helpful. But it does set us up to begin to think about how to work with more complex state vectors that hold more than just, well, it's got 100% of being at position 4, right? Because if we had a state vector that talked about all these positions and had each of these positions having an equal probability of being measured, then we could begin to do operations on this state vector, on this car, right? And instead of just doing an operation on this car that has a single position, we can do an operation on all of the possible positions, right? Because there exists some non-zero probability of them being measured at each given position, right? If this were a more complex example, which we'll see in the next few slides. So like that's state vectors. And I think that's like the whole reason why like we care about state vectors. Like in these cases, it's not super important and it doesn't look like it gives us more information. But since we can treat states on a quantum machine probabilistically, it makes sense to talk about their probabilities and actually operate on their probabilities. And if you were to say that the car is just at 1, well, then like you're kind of vastly reducing the space that you have to work with, right? If we can instead operate on the probabilities of realization after measurement at all of these different states, right? So we talked about simple states, or rather in our example, we talked about states that were just definitively defined with 100% probability of being measured at some position, right? And in quantum machines, we do represent things probabilistically, but that doesn't mean that we can't, in the same way that a classical machine represents 1 and 0, represent 1 and 0, right? And so these two kets right here represent 1 and 0 respectively. And we can go about like figuring that out, because again, we can, in our minds, write the little 0, 0 and 0, 1 down there and see, oh, great, 100% probability of being 0, 0. And the same is true with this one, right? With the 0, 0 and the 0, 1, we've got 100% probability of being measured at 1. And so even though that like these states might not seem to necessitate this kind of like extra 0 or this state vector representation, using them as such begins to prepare us for working with more complex states and representations. And then we can talk about complex states, which is really where this begins to be useful. This idea of state vectors and this idea of like representing a qubit as more than just like what the classical computer says it is, more than just some definitive position, right? But something that's probabilistic before measurement, right? And so by applying the Hadamard gate, we can make this like the 0 and 1 a little more interesting by having this new qubit, qubit 0, with this state vector, which is representative of a 50% probability of measuring a 0 and a 50% probability of measuring a 1. And we'll talk a little more about like why that works. But what happens when we say applying a Hadamard gate, like that's not necessarily super clear. And I want to kind of dwell on that a little. What that is simply applying a unitary matrix, or taking the inner product of a unitary matrix and the states in order to create this like this new state vector, right? And so what's happening is that we've got some matrix defined by these two values or these two scalars within the rows and columns, and zeros, or within the diagonals, I think, and zeros elsewhere. And then we scale these two vectors, 0 and 1, by the given parts and add them together, giving us this like this new ket, right? And this new ket is a state vector that is more complex. It has a little more information than just as 1% probability, 100% probability of being at 1 or 0, right? So now we can talk a little about like measurement and like why that, rather how we can like use that in representation of our states. So like I said a few slides ago, I told you we could have a 50% probability of measuring 0 and 1 each after applying the Hadamard, but it wasn't really super clear as how we did that, right? So we can actually evaluate the probabilities for a state or a position in another state by taking the inner product of the conjugate transpose of the state that we're trying to find the probability for with the kind of like parent state and the absolute value of that squared, right? Which is represented right here. So if we wanted to say, well, let's find the probability of measuring the x, right? Which like it could be 1, it could be 0, it could be more complex, right? We would say, all right, let's change this. Let's apply the Hermitian transposition or the conjugate transpose, which there's a great video there. These slides are in the GitHub, so if you want to check that out, super simple. Essentially, what we're doing is we're converting this x, which is a column vector, into a row vector, and we're taking all the complex parts of that and switching the signs for those imaginary numbers in order to give us this resultant conjugate conjugate transposition, right? So this is now a row, and we can take the row and take the inner product of that row with the state that we're trying to find the probability of with the entire system or the entire state that it belongs to, and then take the absolute value of that squared, right? And so that, yeah, I won't go too much into like the Hermitian transposition, but that's the general form. That video is great, and that's the general form of like finding the probabilities for measuring a given state, right? Hopefully that's clear. If not, feel free to interrupt me. Now we can talk about like normalization and the fact that probabilities should add up to 1, right? Like when we work with probabilities over some random variable, it doesn't really work out if the probabilities do not add up to 1, right? And so measuring the state phi, maybe, I don't know, on the same state should equal to 1, right? And if we have these amplitudes for 0 and 1 that create this state, let's say phi, then it's got to be true that the square root, the square root of the absolute value of alpha squared plus the absolute value of beta squared should be equal to 1, right? Which allows us to have negative probability amplitudes, and it allows us to have probability amplitudes that they themselves do not add up to 1. But when we make sure that the square root of the absolute value squared of each of these probability amplitudes is equal to 1, it guarantees us that our probabilities will add up to 1, right? And so then like a quick note on just like alternative basis. We talk about, like in these previous examples, we talk about like 0 and 1, right? And how, well, it'll, in these cases, evaluate to either 0 or 1. But it doesn't always have to be 0 or 1. There's tons of other bases that can be formed. As long as they're orthogonal, then like you can use them as a basis. And lots of times they will be used in order to kind of increase the space that we can work with. We've got this idea of like global and relative phases within our states, but the global phase is not super important. It's not super important because we can't actually measure it. We can't tell a difference when there exists a global phase versus when there is not. And so global phases will always be complex, and the reason that they'll be complex is because, well, they will not always be complex, but they can be complex. And the reason they can be complex is because complex numbers allows us to find solutions to all polynomial equations. So we can like greatly increase the space that we have to work in to define different states, right? So using complex numbers allows us to define more states, and it makes our quantum computers and our algorithms more powerful. But when we measure a global phase, it doesn't really make a difference. If you notice here, we've got this this scalar I, the imaginary number, times the 1 ket, and that evaluates this ket right here, or this state vector. But if we actually find the probability of measuring x on the state I times 1, you'll see that I just factors out. And when we take the absolute value squared, that I is just lost. And so that gives us this idea that like whether this is a 1 and we're measuring what's the probability of x on the state 1 or x on the state I1, it's going to be the same. And so that gives us this like ability to kind of neglect global phases for the most part, as they're not super important. And the reason they're not super important is it's not going to change the probability of measuring a given state because of what is had here, right? This probability of x on I1 is really just the same as the probability of x on 1. And so hopefully that's clear. Hopefully that gives a little insight. And now we have the observer effect, which can be referred to as the measurement problem, referred to as all sorts of things. But the idea is the same. Once we observe or measure a qubit, we're collapsing and irreversibly changing the qubit to become one of the bases. And it can be 0 or 1, but it can also be any of pairs of orthogonal bases, right? So if we have a complex state with many non-zero elements in the state vector, like it can look like, I don't know, it can be this state, and it can have, like, after applying a Hadamard, just a 50% probability of being 1 and a 50% probability of being 0. But after we measure this Q0, it's going to immediately evaluate to one of those bases, and next time we measure it, there's a 100% chance of measuring the exact same thing we measured last time, right? Because we have lost the entirety of that information. And so, like, we talk about like collapse and the superposition not existing anymore, but mathematically what's happening is you're changing the vector to not contain the same information that it had, right? And so before, when this might have had like 1 over the square root of 2 and I over the square root of 2, it now just has 1 and 0 if we measured 0 the first time, right? And just like a quick note about the IBM simulators. So there's 2 main simulators, 3 main simulators, but I'm going to talk just about the first 2. The quantum assembly language simulator behaves as a real quantum computer would, right? And in a real quantum computer, you don't get to just like peek at the probabilities mid-operation, right? That's considered a measurement. And when you do that, well, the observer effect kicks in and you just ruined or collapsed your state, right? But with the state vector simulator, which we'll work with next week in order to kind of like take a deeper dive into the content that we talked about today, it allows you to actually look at the probabilities, construct these probabilities given the gates, and kind of look at what they should be, you know, what the math works out to, not what the actual like quantum computer gave you. And therefore you can view them before measurement, which is helpful when you're learning, because not being able to view them before measurement just makes it a little more difficult when we're like trying to learn how these things work. And finally, we'll go to the block sphere and how that's used for representation of qubits. There's 4 main steps that I'll talk about that we'll use to kind of restrict our qubit state in order for it to be something that we can look at on a sphere. And when we have a basis of just 0 and 1, we can have a 4-dimensional sphere, and as that grows, we can begin to, as the number of bases grows, we can begin to have like a higher dimensionality on our block sphere, right? And this just allows us to represent more stuff, represent more vectors, or higher dimensionality for our vectors. So like we know from the last part that, or a few parts ago, that we can have these amplitudes, and these amplitudes belong to the class of complex numbers, right? And we saw for the most part, or at least in global phases, that doesn't matter. But like what does matter, what is important, is that the use of these complex numbers for amplitude representation increases the amount of states that we can describe, right? Which, like, awesome, yes, we want to describe as much as we can. But there's no difference between a state with a complex global phase versus one with a real global phase, right? Which we saw like back here with this global phase of I. It makes no difference whether we measure X on I1 or just 1. So global phase, we don't really care about. And so we can kind of reduce this in a form that allows us to have alpha and beta, our probability amplitudes, be real. And then we just add a component to represent the relative phase, right? Which is had by this e to the I5. Whenever you see this e to the I5, that's just representative of the relative phase between alpha and beta. And so we can then put alpha, beta, and phi maybe into the real numbers. I know I said phi for the last one, but I mean, maybe one of them was right. We can put that into the class of real numbers, right? And make our work a little easier, at least when we're hoping to represent this on a block sphere. And then we have the idea that like states must be normalized, right? And so when we have this back here, yeah, the idea of like the square root of the absolute value of alpha squared plus the absolute value of beta squared is equal to 1. We know that like these amplitudes need to be equal to 1 in this case, right? And so what we can actually do is we can use the trig identity of sine square root of sine squared x plus cosine squared x equals 1, and we can kind of implant our alpha and beta into the x, right? And we can say that, like, okay, well, we can then just drop the idea of using alpha and beta, and we can use phi and omega to describe any state, right? And omega will be able to determine, since like sine squared x plus cosine squared x, the square root of that, it needs to be equal to 1. Well, we could say that cosine theta squared and sine theta squared will accurately represent, at least like fitting with this previous identity, accurately represent our amplitudes, right? With e to the I5 representing the relative phase. And so just by tinkering with omega, you get to define the probabilities between 0 and 1, right? And then by tinkering with phi, you get to define the relative phase of the state itself. That's it. That's all I had. And if there's any questions, I would love to hear them. Otherwise, thank you so much for listening and taking the time to come to the meeting.
That was a good presentation. Thank you.
Thank you as well.
Yeah, thank you.
Y'all have a good one.
I hope you have a great week.